And here we are. So welcome to the last video in the climate change section for ASIC 200. And in this video, we're essentially addressing scientific modeling, which is kind of a fancy way of saying, so how exactly are we able to predict what the future climate will look like? And if you want to kind of look at this in terms of a scientific hypothesis, the scientific hypothesis is as follows. These greenhouse gas amounts and increases in temperature will lead to predictable and bad effects to the planet and its inhabitants. Okay, and so just to clarify the statement, it's basically saying the fact that we're emitting greenhouse gases into the atmosphere, and as a result of that, temperatures going up. So that this is something we addressed in the previous hypothesis, but this is actually will lead to predictable effects. So the will is implying that we're getting a sense of what the future will look like. Okay. And right now, if you look at this modeling, the effects are generally, I guess you could colloquially say that they are bad, right? They are bad to the planet and to the inhabitants. And the inhabitants would include us as humans and society, I guess, but also to all other forms of biodiversity in general. Okay, so that's the main hypothesis that we'll be addressing here. So how are we able to future predict? The perfect experiment, of course, as denoted by this goofy paper where somebody has actually tried to use the internet to search for time travelers, mainly because you timestamp things when you actually submit them into the internet, and so by that proxy you can try and figure out if somebody has talked about something that hasn't actually happened yet. Anyway, time travel would be the perfect experiment, because if I wanted to sort of validate or prove what the future is going to be like, then I would build my time machine. I would get in it. I would make sure I haven't forgotten my thermometer. I would go forward, I don't know, however many years into the future that I would like to go forward. I would land in this future timeline. I would come out and I would take a reading with my thermometer. And I would do this as often as I can to as many different localities as possible, right? And in a way, what I'm actually reconstructing is direct temperature measurements, but it just happens to be in the future because I have a time machine, which of course is impossible. So how do scientists do it? How are they actually able to make these very sound and confident predictions about what the climate is going to look like? And because we know that they can, because decades ago the predictions they were making are actually turning out to be true as far as what's been happening lately. So how do they do that exactly? Well, at the core of this is to realize that fundamentally a lot of science is very predictable, right? So you have theories and you have laws, and these are things that by and large have really stood the test of time. Okay. Now, laws in particular, a lot of them are actually denoted by mathematical representation, and because of that, you can sort of calculate predictability. Like the classic example would be, I guess, the gravitational pull, right? So if you think about it, I can actually predict the future. If I have this block here, okay, and and I drop it, right? Due to the law of gravity, right, or the gravitational law, I can actually predict the future. I know what's going to happen. I know if I let go, it's going to fall. Not only that, if I actually measure the distance between where my block is and where the floor is, I can actually predict to a very precise and accurate degree when it's going to hit the ground as well. So if you think about that, this is sort of what, you're able to do with sound science, right? You're able to take these mathematical representations of physical properties in the world, and from that you can actually make very sound predictions. Now, in terms of mathematical properties and how they relate in particular to climate change, well, then the big one, of course, is the one that we talked about in the last video, and that one is the first law of thermodynamics. What I have here on this slide here is, we talked about what it's called, the first law of thermodynamics, and we said colloquially, you could say it's the conservation of energy. Well, what you're staring at right now is kind of the mathematical representation of what the first law of thermodynamics is. Okay, and this is actually the chemistry way of depicting it. Physicists will tend to use the same equation, but there's a plus sign here instead. And this is basically, there's these three sort of lettered symbols, but what they actually denote is different forms of energy. And again, the key thing here, if you remember, because the first law was all about the conservation of energy, what this is actually saying, this is just a bookkeeping equation. It's kind of saying that all these different types of energy must add up. Right? They have to add up. Whatever happens, if something happens here, it's going to affect that bookkeeping, right? So this is sort of the way you want to view it, okay? Now, if you want to kind of get specific about what these different terms means, then take a look at this slide where we've sort of labeled them specifically. So we have dU here, which stands for internal energy. We have dQ here, which stands for heat energy. And we have dW here, which stands for work energy. Okay, and the D actually means changes in. Okay, it's actually short for differential, if you'd like. Okay, so this is just saying that the internal energy of a system is essentially equal to the amount of heat and the amount of work that's going on within that system. Okay, so there are those words again. System, if you recall, we're talking about below the tropopause in the troposphere when it talks about our planet, and essentially all of these things have to add up. Okay, now if you think about it, I think something like internal energy you might not have heard of before, and work energy you might not have heard of before. But if you look at something like heat, then heat obviously is something you kind of get. And hopefully you can also see that when you're talking about what's happening in our particular planet and what's been happening ever since the Industrial Revolution, because of those increases in greenhouse gases in the atmosphere and the concomitant rise in the global average temperature, then hopefully you can see that the change in heat energy in our system overall has gone up. So just imagine that for this part of the equation, dQ is going up. Okay, and that will manifest itself in a number of ways, but probably the most obvious is the fact that the planet will just get hotter, right? And again, don't get confused with the term weather. It might not be getting hotter where you happen to be, but it's getting hotter if you take that global average of what's actually happening across that entire system, the system being the Earth below the tropopause in that troposphere. Okay, and if you think about it, all of the other things you see in climate change kind of make sense now, right? Because if this goes up, and remember, energy cannot be created or destroyed, but it can move around, or it can be converted into other forms. So you would imagine that if the entire system has to stay the same, but now that there's more energy because of this increase in dQ, then some of the other places where you might see a change would be as follows, right? So for instance, maybe you see a change in the amount of work energy in the system. So if there's an overall increase in work, and what is work? That's kind of like the ability to move stuff, right? And if you think about the planet and you think about moving stuff, well, consider the following. What happens if you move air? Right? If you move air, what you get is wind, right? And I have this great graphic over here, which I'm just going to bring over. Okay. So this is actually a wind map right now with the United States, and it's actually showing you, based on local direct readings, what the wind is alike in these particular areas. And you can see the legend here. So where it's really white is basically really windy. And you can kind of see that if you kind of get into Southern California, it's actually quite gentle. But in a lot of other places in the US right now, it's a little bit, it's quite windy, right? And so this is just an example of work energy. It's like air and you're moving it. So it's actually, you actually have to expend work energy in order to get it to move. Another example of movement is what happens when you move water. And for that, I've got this gorgeous video from NASA. So I'm just going to play this. I find this quite mesmerizing. So I'm going to just play it for like a minute or two, and you can just kind of watch. But this is essentially tracking water movement for about a 2-year period. But it's just outstanding. Here, take a peek at this. Note all the water currents at the south of Africa. That's why that's such a hard place to sail. And you should note that a lot of these sort of patterns are influenced or partly propelled by the wind pattern that you see globally, as well as sort of the topography of what the ocean looks like underneath. Kind of wondering why we don't tend to see things like hurricanes, it's primarily because of the wind patterns on the west coast, as well as the topography below the seabed is kind of suited for that way. All right. Right, so that's a manifestation of work energy. And if you think about it, if you're looking for media reports, this is why on average, if you take a global mean of what's happening on our planet, you see that there's more extreme weather events, right? Because often extreme weather events are things like storms, right? Or hurricanes or cyclones or what have you. And so this is actually an example of work energy, okay? The other thing that you can kind of look at is this internal energy stuff. Internal energy is actually kind of a complicated term. It's sort of implying things like, certain atoms or certain molecules will be more energetic because of those states that they can exist as. But one other way, an often simple manifestation of what internal energy might look like in a system is if something happens to have more kinetic energy, i.e. it wiggles a lot more. And so if you do have this bookkeeping, and one of the things that can go up is this du value, you can say that sort of an intuitive manifestation of an increase in the internal energy of something like water, right, is to see it undergo through its changes in states of matter, right? So in terms of actually what's happening intuitively, that could translate to things like, ice caps melting, right? So that's a change in states of matter. Or the other thing that could be happening is the situation where water is evaporating, right? So you see that sort of in certain tropic bands where drought is being a serious issue right now. And this is just to say that, again, because we can measure this dq value right now, because we have that value in terms of the direct measurements, in terms of the ability of what CO2 is able to absorb and then re-emit back to the surface of the Earth, because we have this number in this equation, we can actually start to formulate predictions about what might happen with these other instances. Okay, so now at this point, you're probably, I would imagine you're thinking, okay, I kind of get it. I've got this equation here. If I can measure the amount of extra dq that's in my system, then sure, I can see how that can translate to these funky effects that we see manifest itself in work or internal energy or what have you. But it's still kind of too vague. Like, how does this equation predict future climate, right? And the short answer to that is that it's, you can sort of work on this equation and sort of re-express it so that you can get at the specifics, like the actual specifics of what happens to the air. How will it expand? How will it move? How will it affect other packets of air that are adjacent to it, right? So you're right, this is a very simplified expression for that first law of thermodynamics. But you can take in all sorts of other physical laws, sort of scientific laws that also have mathematical representations, and use those and sort of recombine them with things like this first law of thermodynamics to actually get at that more specific take of what the future is going to look like. A great example of that is this equation. This is another fundamental one. This is known as Boyle's law, and this is essentially a great mathematical expression that essentially will describe physical characteristics of gases. Okay, when you're looking at gases, it's basically telling you that the pressure that gas can exert, right, times the volume, the amount of space the gas will take, is actually going to be equal to the amount of gas, like the number of molecules of that particular gas, times the temperature, times this constant that kind of brings it all together. Okay, so this is known as Boyle's law, and this is just another example of the high predictive effect that scientific laws, mathematical representations of, I guess, physical effects in science can sort of allow you to make predictions. This is kind of telling you that, okay, if I have pressure times volume is equal to the amount of stuff I have times the temperature, then if I always have the same amount of stuff and I increase its temperature, then that means that number will be bigger over here. So therefore this number must be bigger as well because it's equivalent. So maybe you see that as an increase in pressure, right? Which makes sense. There's more temperature, so things are moving around more. That's going to exert greater pressure. If the pressure is sort of relieved, like it's allowed to sort of exert itself out, then obviously that's going to manifest itself as an increase in volume, right? Actually, here what I'm going to do a demo because this is one of the perks of having a lab, is that you can just buy liquid nitrogen whenever you want. And so let's shift over to a demo right now. Okay, so we're gonna do a quick experiment, and what this experiment will entail. So essentially we're gonna try and demonstrate Boyle's gas law, Boyle's law, and just show you how some of these laws do have very strong predictive capabilities. So let me just blow this balloon up. I got a balloon, and just because I have two of them, and balloons are always fun, I'll do another one. Okay. So according to Boyle's law, we have PV equals nRT. So pressure times volume is going to equal to the amount of stuff inside this balloon times a constant R times the temperature in RT. So obviously the amount of stuff is not going to change because I've trapped it in a balloon. And right now the ambient temperature in my room is, I guess it's close to 22, 23 degrees. And so essentially we're going to see if we can adjust the volume and pressure just by changing the temperature. And what we're going to do is we're going to use liquid nitrogen because I have some here. So I gotta put on my heavy duty glove. Okay, it's evaporating really quickly. Okay, so the premise is if PV equals nRT, right? And essentially on that side of the equation we have N, amount of stuff, times a constant, times temperature. If I lower the temperature down, that means that value is going to get smaller. So because of that, we would expect the other side of the equation, P times V, to also go down. And hopefully that will manifest itself both in terms of pressure, the amount of pressure that the stuff inside can exert outwards, and also the amount of volume. So this is why the balloon will get smaller. So I'm just going to put it in here. I'm trying to do this carefully. I don't know if you can see it go down. If you ever want to be the coolest person in a kindergarten class, you bring liquid nitrogen, because then you can do stuff like this. So you can see it's shrinking, right? So this is actually Boyle's law manifesting itself. Shrinking. Right? The pressure and volume is going down because the temperature is going down. Okay, I don't know if you can see it, but to me it looks a little bit like this right now. And so if I take it back out, that means the temperature is going to go back up, and that should mean that the other side of the equation should also go back up, so the volume and pressure would go up. Now, even though this is kind of goofy and just kind of cool, so I'm going to show it to you here. So here's one. Temperature is going up. So therefore, pressure and volume needs to go up. So this is Boyle's law in action right now. See, you can see it extend out. Right. Put that here. With my fancy glove. Here's another one. You can see it's getting bigger and bigger. All right, cool, right? And so really, like, the point of this demo is not just to show you how cool liquid nitrogen is, but the Boyle's law is super useful, right? So you can imagine that if you're trying to use this from the point of view of making predictions around climate, and particularly around how the gases in the atmosphere behave, then you have this law where you can actually make some very strong mathematical predictions about what's going to happen, right? And it's not just a case of, oh, it's going to get bigger, it's going to get smaller. You can actually calculate exactly what's going to happen. And so because of that, it's laws like this in combination with, say, the first law of thermodynamics, and in combination with all sorts of other laws around how fluids work, how gases work, how temperature travels, and things like that, that you can actually make these very strong predictive climate models, okay? So we'll leave it at that, and I'm going to put this back down, and I'm going to play with this for a little bit more. And, by the way, here is the actual mathematical representation of the first law of thermodynamics as defined for atmospheric type calculations. And the thing, just so you know, this particular equation is not something you need to know. But if you kind of look at the letters here, you'll see that Boyle's law is actually sneaked in to some of the symbols into this particular representation. Okay, so now, you don't need to know this equation, but I would like you to focus a little bit on sort of the graphic just behind the equation. And what you can see here is a whole ton of cubes that have been stacked together. And what I want to point out here is that if you think about it, if you wanted to model, say, the behavior of gas under these larger scales, and you want to do it where you're able to look at these individual cubes and how they affect each other, like how they affect the ones that are next door and the ones that are on top and so on. Because you can imagine that as the volume goes up or the pressure goes up in one of those cubes, that's going to affect what's happening to the adjacent cubes, right? And I guess my point here is that if you are trying to model this type of behavior, looking at something where you do have this sort of larger scale with this higher resolution, where you're actually looking at these more defined bits and how they interact with each other. This is not back of the envelope calculation, right? So this is totally different than, in my demo example where I was, focusing on what's happening in the balloon. That is back of the envelope calculation, right? Because it's very simplified. But when you're looking at something here where it's sort of a grander scale, it's like a chunk of atmosphere, or heaven forbid, the system, everything below the tropopause, hopefully it makes sense that when you devise these climate models, it's a little bit more complicated. And this is where you kind of get into the idea of what a climate model or an Earth system model actually is. So I do want you to pause here momentarily just to read this sort of, official definition from the assessment report number 5. So you can kind of get a sense of the lingo behind it. But really, once you finish reading it and you come back, the key thing that you want to kind of focus on here is actually what I've written down in this black section. So I'm just going to read this out loud because this is kind of key, and it brings up the word algorithm as well. So models are composed of algorithms, which are step-by-step calculations, which in turn are based on processing mathematical representations or expressions, which in turn are derived from physical laws, which in turn are derived from the things, i.e. scientists, people see and do and measure every day and throughout history. So this is the concept of an algorithm, and what I'm trying to say here, though, if you have an algorithm, you're not, it's sort of like a stepwise calculation, right? For instance, you figure out Boyle's law for this packet of air, but that will actually affect what's happening next door, so then there's a stepwise calculation of what's going next door, and so on and so on and so on. So this is kind of what a model is all about. And as you can imagine, this is primarily fueled, if you like, by the awesome power of computers. And this is actually reflected in this next slide here. I won't spend a lot of time here, but you can kind of pause and look at it yourself. But this is actually just showing you that as computers have gotten more and more powerful, as the computational possibilities are more and more dense, if you'd like, you can actually see that these models are getting more and more complex because they're able to feed in more and more different nuances and more different variables. So for instance, if you look at this figure here, this is actually kind of showing you that when they first started releasing these types of assessment reports in the mid-1970s, the models were actually quite simple, right? They only took a couple things into consideration and really not to a heavy degree, right? But as time goes by, as you sort of released these other itinerations, I guess, of these assessment reports. You can see in the last one, which was just released just a few years ago, there's a lot of other things that they take into context when they're actually trying to figure out what this climate model, what this future projection is going to look like, right? It's not just the top three, the atmosphere, land surface, and ocean, and sea ice, but they can also consider, right, the behavior of aerosols, how the carbon cycle works and how things cycle around, the vegetation, chemistry of the atmosphere, as well as, sort of the nuances involved in land ice. Okay, and this is another way to look at sort of the increase in computational power. You can also see here that as time has gotten on, the resolution has gotten a lot better, i.e. the computers can actually handle calculating these smaller grids, if you like. And so that kind of gives you a sense. Now, one thing I do want to point out that just because the more complicated the model is doesn't mean it's better, because ultimately the best models are the ones that actually fit reality. So but this is just to show you that over time, as we learn more about the behavior of these climate processes, as computational power increases so that we're actually able to do more sophisticated algorithms, you can see actually that these climate model projections are getting more and more higher resolution. Okay. Now, another important point I gotta bring up here is that you have a community of climate scientists, right? And quite a few of them are doing things like future projection, climate modeling. And hopefully it makes sense that if you have this community of scientists that are stationed throughout the world in different places and different universities and different research centers, they need some sort of standardization, right? So if they're going to predict the future, they need to agree on a set of parameters of what that future might look like. Okay, so in other words, if scientific group number one, does a modeling experiment and says that this is what it looks like when CO2 reaches this level up to 2100, and then scientific group number two says, well, we're doing this climate modeling sort of calculation, and it's actually dependent on a different degree of CO2 emissions by 2100. Now, even though each of those individual sort of research outputs would have value, hopefully it makes sense that you've kind of lost some synergy, right? Because how great would it have been if they had both agreed to look at similar emission scenarios so that they could actually look at their data together to see if there's any agreement, to see if there's any additional insight that comes about from being able to look at two things at once and things of that nature. So scientists are a smart bunch and they recognize this, and so because of this they have actually standardized what we call emission scenarios, and actually what we call them now are representative concentration pathways. I have trouble saying that for some reason. Or RCPs, okay? Representative concentration pathways, or RCPs. Now here's another slide that I highly recommend that you just sort of stop and pause for a minute, just kind of read through. But this is actually just defining the fact that in general, almost all scientific literature, when they do climate modeling and they take into consideration what an future emissions scenario might look like, they sort of fall back on 4 of these RCPs, and they are RCP 2.6, 4.5, 6.0, and 8.5. Okay, and these numbers, the 2.6, the 4.5, 6, and 8.5, represent extra watts per meter squared in comparison to sort of this baseline number that was derived from about the 1700s, the mid 1700s. Okay, so if you want to sort of colloquially describe what these RCP representation pathways or representative concentration pathways are all about, RCP 2.6 is basically we're really good, right? We're able to do something where we essentially at this point in time we've really knocked down fossil fuel emissions and kind of like the environmentalists' dream scenario. 4.5 and 6.0 are a little bit more in line with projections if we do our best to be good, i.e., for instance, if some of these international treaties or international agreements come into effect and are actually followed, we will kind of sort of limit the RCP scenarios to something similar to 4.5 and 6.0. And RCP 8.5 is sort of this number where, okay, screw it, we'll just carry on business as usual. And if you kind of look through the data of the IPCC report in the assessment report number 5, and you kind of see graphs that show you, oh, this is what things are going to look like at RCP 2.6 or 4.5 or 6 or 8.5. You always see that kind of the more detrimental effects are happening with the higher number of RCPs. Okay, so that's the other thing to kind of put in the back of your mind. But I guess the key thing here is if you think about it, the reason why we can predict the future is ultimately we're being very clever in how we apply these scientific laws, right? It's kind of like one giant computer simulation where the parameters are more or less defined by reality, by fundamental universal laws of science, right? So it's kind of like, it's a little bit like the movie Matrix. I don't know, do you remember the movie Matrix? You remember the movie with Keanu Reeves and the crazy slow-mo kung fu stuff? Anyway, so climate simulations, the modeling that predicts the future, is kind of analogous to what's going on in the Matrix. It's like it's one giant computer program, or multiple mini computer programs trying to reflect what will happen in the future. Okay, so Matrix is obviously a bit different because it's not real, because it's also trying to predict things like human behavior and stuff like that. But the climate stuff is real. In fact, what you say it is, or how real it is, is dependent on whether you can validate a model or not. And so this is kind of like the final thing I want to kind of go over in the climate change lecture, is what does it mean to validate a climate model? Like, how are you able to sort of achieve this element of confidence in what this future projection is telling you? Okay, and so there's a number of different ways you can validate a climate model, and in this slide we've got three biggies. Okay, and these are actually worth knowing, but they are as follows. So the first way you can validate a model is actually to generate it and then watch it go. Right? Watch it go for a number of years and actually see if what's happening in that interlude from when you first created it, during that timeline as it's allowed to happen, whether reality actually fits what the model is suggesting, right? So this is actually done quite often, because a lot of climate models that are out there have actually been running for many, many years, decades even. And so from that, you can get a sense of your confidence in that future projection, because you're actually seeing whether that future projection actually turned out to be real. Okay, so that's one way of validating a climate model. The other way, the second way of validating a climate model, is that because it's all based on sort of these fundamental laws of science, which again have these mathematical representations, then technically speaking, if a model works, you should be able to run it backwards as well, right? So if you can run the model backwards, inputting the data for example, the CO2 amounts in the air, and actually seeing if you do that, and by running it backwards, you can actually get data that coincides with the past measured temperature data that you already have, right? So that's another way of validating it. The third way of validating it is actually something that's a little less common, but occasionally, every now and then, there are sort of these major events on the Earth that kind of allow scientists to just sort of see whether the models, how do they react to them. So, for example, we might have a major volcanic eruption which just sort of spews all sorts of particulates into the air. That's actually a great way to really strain and test the model to see how well or how robust it is. Another good example was actually after 9/11. There was sort of a no-fly ban, and essentially all of a sudden all the contrails that planes would normally leave were not there, right? And so here's another opportunity where you kind of had this perturbation, this major perturbation in the global sort of atmosphere, and you were able to use that as an opportunity to sort of test how robust your model is. And if it worked, if your model was able to perform well even despite this large perturbation, then you can also say that's another degree of validation. Okay, so ultimately there are ways to kind of get a sense of how good your model is that don't rely on a time machine per se, but this is kind of why there's a lot of statements out there in the IPCC report in particular that are actually quite strong, in that folks are actually very confident about what these future projections are actually saying. Now we'll get into this later, but let me just end here, and this is actually very important. Okay, so I've just highlighted this statement down here. And although there are many different climate models out there, and there's various papers published, all the time essentially, that are trying to use this methodology to try and see what things might look like in the future. Some of these models are actually quite simple. They just focus on a few things. Maybe the resolution isn't as great or as finite. And other models are actually very complex, where the resolution is very small. They actually do take into consideration all sorts of things. And it's sort of a rookie mistake to assume that the more complex the model, the better it is. But in reality, the best models are simply the ones that are best validated, the ones that will fit reality. So that's another thing to always take into consideration. Okay, so in any event, I think I'm going to end here because when we come back to class, we're going to go over the IPCC report and we'll talk about specifics at that particular session. So for now, I'm just going to say bye-bye.